which is, well, what kind of things can you do with a Kinarm? And probably the most basic feature and something that is used in every single experiment and paradigm is to monitor what your subject did. I mean, that's the whole point of research, is to analyze people's behavior. In this example, it's a very simple example. The subject was presented with red targets and they were told to reach from target to target. So this is, for those familiar, just visually guided reaching. It's a very common paradigm. What's important here is the subject is moving from point to point. The robot is not applying forces. The robot is not moving them. The robot is being moved by the subject. But because it's got motors and therefore it knows where it is, we can record where it moved. And since the subject is grasping the handle of the robot, that means we know what the subject's behavior is. So again, this is really probably the most important thing that the Kinarm does, is it measures what your subject did so that you can afterwards analyze it and make your inferences from it in terms of your experimental paradigm. Now, I do want to point out that this paradigm is obviously a very simple paradigm, and there's lots of other things, as I'll get to a bit more later on, that we can present more complex graphics. When you go to program your task, you have complete control over the timing and choice of visual stimuli. Even though only one arm is being moved here, you can monitor both arms simultaneously. And if you had an exoskeleton, you'd be able to monitor shoulder and elbow joint as well. Obviously, with the Kinarm endpoint robot, you only can monitor where the hand is, because that's all you have connected to the robot. The next valuable feature of a Kinarm is that you can use it to actually move the subject. And in this case, I'm going to be talking about something called position control. The example shown here is what's happening is that in this case, the robot is actually moving the subject's hand. So a trajectory was programmed up, and the robot moves the subject smoothly from one point to another point, and that's what's happening on the right. It turns out that in this example, actually, the subject was instructed to mirror match with their left hand. So the robot is moving their right hand. The subject is then moving their left hand to mirror match it. So this is actually sort of a nice example of both what's happening, what I'm talking about in this slide in terms of moving the subject, plus the previous slide, which is monitoring the subject. The example shown there shows nice smooth trajectories because that's what was desired for that particular paradigm. But that's not something that we constrain. So if you're going to make up your own task and you have a paradigm that requires something different, you can create the trajectories to be any shape you want. They can be straight or they can be curved, and you can change the time profile as well. We don't constrain you. You can set up the trajectory to be any shape and waveform that you desire. This next sort of basic feature is similar to the previous one, but there is some subtle differences. And so I've called this Perturb Subject, and in this case, it's torque control. In the example, the subject was reaching from one target to the next target, and then when the second target turns on, you can see there's a perturbation that's moving the subject's arm off to the side. Well, how is this different than the previous one? I mean, in both cases, the robot's moving the subject around. The difference is, what is the robot controlling? In the previous slide, I had called it position control because the robot was trying to control position. Here, it's called torque control because the robot is controlling torque. Okay, well, what do I mean by that? Well, let's imagine you've got a subject with a very relaxed arm. For the position controller, if you're going to move a subject from one point to another point and their arm is very relaxed, it's going to take very little force to do that. This is what the robot is doing, is the robot is trying to move through a trajectory, and it's just figuring out, well, how much force do I need to? Oh, I moved, they apply a little bit of force and it sees, okay, I'm getting close to that position. And so It doesn't need high forces if the subject's very relaxed, but if the subject is co-contracting, for example, resisting the movement, then the robot is going to increase the forces because it's trying to get you to a certain position. With torque control, it's different. The robot is been programmed to apply, for example, say a 2 Newton meter torque at some joint, or with the endpoint robot, you can talk about forces. So let's say it was a 10 Newton force in the upright direction. It doesn't care where the subject's arm is. When the subject moves, it's still going to be the same, 10 newtons up to the right. In that case, if you have a very relaxed arm, what's going to happen? Well, then the 10 newtons is going to cause the arm to move a lot, because if your arm is very relaxed and somebody knocks it, it gets moved. In contrast, if you're very rigid, what's going to happen? Well, it's going to be a very small movement because you're resisting that movement. But there's still going to be the same amount of torque applied. So again, with position control, what is being controlled is position. So it's going to make sure that it always, tries to follow the same position, and you might get very different torque levels depending on subject behavior. With torque control, the torque levels are always controlled, but the positions might be very different, again, depending upon subject behavior. Does that difference between position control and torque control make sense to people? All right. Couple other things just to mention, and this is sort of similar to the theme I mentioned earlier, which is you have complete control over the design of any perturbation you apply. We don't limit you to square pulses or any particular waveform or amplitude. You can, if you want to apply a force or torque perturbation, you decide what the waveform looks like. And again, if you had an exoskeleton, you can actually apply these perturbations in a joint-based coordinate frame rather than endpoint-based. You can also create things like force fields, and one of the examples that we give is a spring. Spring, of course, means that you've got force dependent upon position, and so you can see in this example that as the subject pulls their hands further apart, the spring produces, or the virtual spring produces forces that then pull the hands back together again to a certain rest length, in this case of about 15 or 20 centimeters. So this is just what we call a haptic spring. In this particular example, we also added sort of the visual illusion. So we drew on a visual rendition of a spring to match what's going on with the forces. And this actually creates quite a powerful illusion. As I had mentioned this to Alex during the installation of the Kinarm. This is a demo that we provide all of our customers, and we suggest that they always keep it ready, because if anybody is coming by to see what this new Kinarm is, what is this thing, you sit them down. This is such a simple thing because they can just sit in there and feel it. There's no instructions or experiments, and everybody loves it because it just feels so cool. And part of it is it's not just how it feels, but also when you see the spring there, your brain just creates this illusion that there really is a spring there. Some related force, or some other force fields, I should say, that are commonly used. One is a viscous force field. So viscosity is a force that is proportional to speed, but in the direction opposite movement. So if you move slow through the viscous force field, the forces are low, but the faster you move, the more you get resistance. So it sort of feels like you're moving through molasses. Another common one that's used particularly in learning experiments is a curl field. So for those of you who've taken various levels of physics and engineering, you might have be familiar with curl fields in terms of how they work with electromagnetics. But for the rest of us, you don't really encounter curl fields in the real world very often. And that's why it's often used in research, because it is novel to the vast majority of people. What happens is forces are created that are proportional to speed, but perpendicular to its direction. So if you start to move straight out from you, it'll push you, say, off to the right. The forces will. So then as you start moving off to the right, the direction of those forces is going to change with your movement. So it'll start pushing you back towards you. And eventually what happens is it ends up making your arm want to curl around in an ongoing circle, which is why it's called a curl field. You can also create interactions between the arms where the force on the left arm depends on the movement of the right arm. Spring is obviously an example of that, where both arms are doing that, but you could have just one that influences the other. You can create things called force channels. This is a paradigm that started to become popular about 10 years ago in the field of sort of basic research and motor control, where what's happening is that forces are restricted to movement in a narrow channel. And so it feels like basically you're constraining movement to sort of 1 degree of freedom, which is kind of an interesting paradigm. And last, again, if you had an exoskeleton, you can create various force fields in a joint-based reference frame. You can also develop tasks to start analyzing more complex behavior. So what I showed you earlier are just sort of very simple things, simple reaching, but you could create something. And so this example, the subject was instructed to hit some of the faces, but not other ones. And the point here is just to show that you can start to do things like, to have visual stimuli that move around and different, depending on what they look like or not, you can have the subject perform different behavior. You can't tell in this case, but the subject actually gets a little bump every time they hit one of those faces, so they get a little bit of haptic feedback in there, so it feels like you're actually hitting something. So there's lots and lots of different possibilities. You basically have control to present whatever sort of visual or haptic stimuli you want, and they can be driven by or their behavior can be changed in response to any kinematic or other input that's measured or controlled by the system. So there's lots of possibilities here. I'd like to just show, oh, sorry, I noticed someone else is in the waiting room. Visual stimuli, so I've shown some very basic ones like, circles and stuff, but one example that we enabled a couple of years ago is the ability to create paths. And so there's really, there's thousands of line segments. You can create polygons of up to, I think, about 25 different vertices. And you can also create situations where there's, hundreds of different moving targets. So even though a large number of people's paradigms are based on quite simple visual stimuli, don't feel you need to be restricted to that. There's a lot of different possibilities available here. Just so you know, there is an optional gaze tracking module that we sell. This is the Kinarm gaze tracker. It's a heads-free system that goes at 500 hertz. It can be, purchased after the fact and integrated into the system. For those of you who maybe not sure how gaze trackers work, basically they work in the infrared spectrum. So there's an illuminator that basically provides a bright amount of illumination in the infrared spectrum, so the subjects can't see it. And then there's a camera that then has a nice bright view of the subject's face. And both of these need to have their view basically bounce off of, there's a very large mirror put underneath the display, which reflects infrared, so that these cameras and illuminator can bounce off a couple of reflections before looking at the subject to get a good view of it. This is something that is fully integrated, so it becomes controlled and part of the Kinarm Lab in terms of the calibration, the setup, the data collection, its ability to control the system. So it's a very nice optional feature that can extend the capabilities of your lab. If you were to have this system, this is an example data that I showed earlier, but now showing where the gaze tracking is, and of course this little green hash mark that's flitting around is where the subject is actually looking while they're performing the experiment. One caveat I will add is that the gaze tracking region is limited to the middle part of the workspace because of the way that gaze tracking works. As I mentioned earlier, Kinarm Gaze Tracker is fully integrated, so that means that the subject's gaze can be used to drive system behavior if you were to get this module. You can also create different sort of haptic interactions. It's always hard to sort of see a haptic interaction on a screen, but there was someone moving around in these different areas, and so this is just what we call a cobblestone region. So it felt like they were like, you know, if you were dragging something over cobblestones, you can create virtual walls, so it feels like you're sort of trapped inside a particular region. We'd integrated a curl field in just part of the workspace, not over the entire workspace, so that's why the subject was moving in those different ways. And so there's lots of different kinds of interactions that you can create. We give you access to the underlying kinematics, so the positions and velocities, acceleration. You have access to the commanded torques, so you can program anything that you want up that relates those two in any way, which really gives you a lot of flexibility. Just so that people are aware, you know, if you're reading various papers and you come across someone who's using the Kinarm and you're like, well, how are they studying posture? What's going on? Well, we actually have an option for studying posture, which takes your Kinarm Lab, Kinarm Endpoint Lab, and puts it on an adjustable height configuration that goes up and down and adjusts to the subject's height while they're standing on force plates. So this now means that in addition to studying what's going on with the arm and reaching, you can also look at postural stability and control at the same time. Again, if you were to get this option, everything is fully integrated, and so again, the data is captured it simultaneously. It's available in real time to control your experiment. So it really is a fully integrated solution. And there's lots of other technologies that people can interface with. So you guys have an analog and digital data acquisition card in there. And this is an example of somebody who was making use of that and was recording EMG and what was going on. And I'll just click play on that. Or I'll try to click play on that again. The subject reaches from one point to another point. And in the second trial, there's going to be a perturbation. And of course, right when they perturb, this is the EMG reflex response that was recorded by the analog inputs. So those analog inputs are, and the digital inputs are connected to the real-time computer. So again, this is an integrated part of the system, which means that you can, again, not only have the data in all the same data files, so everything is all combined together, but it means that you can use these to drive system behavior in real time. So EMG is the most common sort of peripheral technology that many of our customers make use of, but we have had others that work with EEG systems or transcranial magnetic stimulation. I mean, really any technology that accepts digital or analog inputs or outputs can be interfaced with our system through those different interfaces. Just mention briefly some examples of other paradigms that various customers have used over the years, again, just to get you thinking about different things that can be done with the Kinarm. I talked earlier about how for most of our customers, it's really important that the visual and mechanical worlds are spatially aligned, because of course, if they're not aligned, then that means you're going to be doing something that's using part of the brain that deals with misalignment. Well, sometimes that might be what you're actually interested in. And so even though there is this semi-transparent mirror, there's a vision blocker underneath there, so you can actually block vision of their hands, which means that you can then start to provide, feedback about where the robot is, but you actually change it. You manipulate it, so it's not actually where the robot is. So you actually dissociate the visual feedback from the actual mechanical world. The visual motor rotation task is a classic example of this paradigm. I bring up force channels again because this is again a paradigm that started to become popular with robotics about 10 years ago in certain areas, and so for certain types of questions, this force channel is a very useful paradigm. I've talked about different loading conditions. What I didn't mention is that you can combine these in any way that you want. As I mentioned earlier, when you program a custom task program, you have direct access to the torque outputs. So we don't sort of say, oh, do you want to use this load or do you want to use that load? We don't specify it that way. We say, you tell us what you want the torques or forces to be, and that's what it's going to be. So you can create and combine any sort of loading conditions that you want in any way to create a force or torque command. So we don't limit you. Similarly, just sort of repeating what I mentioned before, that there's all sorts of complex visual stimuli that can be used. Most people use static ones because from a paradigm design perspective and a data analysis perspective, that's often the simplest and most robust. But there are certain paradigms where you need to have the visual stimuli moving. You need to be able to control them either through something that was pre-programmed or in response to behavior, and we allow that completely. Another way of wording that is that any input can be used to control any output. So what are the inputs? Obviously, position of the robot is a key input, and that of course then leads to velocity and acceleration. So you can use those to drive system behavior. But the analog inputs and digital inputs are available, again, in real time. So you can use those to drive system behavior. If you had an optional gaze tracker or the force plates, those can be used to drive system behavior because all of these inputs are available in real time. In terms of outputs, the most obvious one is the forces on the robots, because of course these are robots. That's the fun part of having a Kinarm, is that you can, manipulate what your subject's doing. So that's the most obvious one. But of course, visual stimuli are another form of output, and most experiments are driven by some sort of visual stimuli, which you need to be able to control it, often based upon subject behavior. Likewise, there's analog outputs and digital outputs, so those can be used. You can connect speakers, for example, to an analog output, so you can drive sounds to be part of your experimental paradigm. So there's lots of different options available. I'm just going to mention again a little bit more, just this one slide on Kinarm standard tests. As I mentioned earlier, this optional feature was designed and aimed more for the clinical research market. And the value of having something standardized is, of course, it means that if you do an experiment and collect data here, and someone else in another lab, another part of the world is using the same standard test, it means that your results are directly comparable. And so we have come up with a suite of tasks that we call Kinarm standard tests that includes these predefined tasks where, again, everything is predefined. There's automated analyses that have been designed to pick out sort of key parameters from these various tasks, and then they can be output to create neurological reports with comparison to normative data. So we have normative databases ranging between a couple hundred and a couple thousand subjects of all ages. And so again, this is a very powerful tool. The number of tasks is growing. The number of people using these is growing. And like anything that sort of becomes standardized, the value there is your ability to compare to what other people have done. And to not have to go out and collect your own normative data is also very nice. In terms of our customers, what are they doing with Kinarm? What kinds of fields are out there doing it? And so the first I'm going to just mention is robots for clinical assessment. This is certainly a large growing area. Many of our customers are interested in different neurological indications, stroke, multiple sclerosis, Parkinson's, Alzheimer's, and the list goes on. And so we have been involved in a clinical trial where they were trying to use using the Kinarm as an experimental measure for assessing what was happening with the therapeutic intervention that they were trying to provide. Many of our customers are interested in understanding or looking at motor reflexes. Various ones looking at limb mechanics, which really more requires the Kinarm exoskeleton, so you can actually understand how the limb is moving. Basic understanding of motor control, how do humans control their arm movement, and how do they learn to adapt into their environment as things changed. This is obviously very much related to the neural basis of voluntary control, but what we're really getting at there is that we do have versions of the Kinarm. In fact, the original Kinarm was made for non-human primates, where they are recording neurons directly. And so this is actually another very powerful use of the Kinarm, is to translate ideas and things that were developed based upon direct neural recordings with non-human primates, and then moving that over to the world of human research, and then it can go the opposite way as well. And the last field that I'll just mention is eye-hand coordination. So customers who have purchased the gaze tracking option can of course actually relate arm movements to where the subject is looking. If you really want to get a better sense, I would highly recommend looking at various publications. The company, of course, we don't do research. All of our customers do the research, and so that's where the fun stuff is. And so you can go look. We try to keep our list of publications up to date. That's getting more and more difficult as our customer base grows. But at the very least, it gives you an excellent starting point to go see, okay, what kind of different things are people doing, which labs are sort of active in different areas, and that can really, I think, help broaden your idea of what kinds of things Kinarm can do and how it can be used, because it's really fun for us when we get to see the Kinarm being used in different ways by different customers. Even though we try to anticipate, there's the fun part of research, of course, is people are always doing something new and interesting.